Welcome to today's Research Pays Off. I will hand it over to our speaker, Jeff Roesler of University of Illinois Urbana-Champaign.
Thank you, Lauren. And I'm going to go ahead and share my screen. Appreciate the opportunity to present some of the findings we had for this Illinois Department of Transportation, Illinois Center for Transportation Research Project. And so if we get started here, I'd like to thank the researcher who helped me on this, Dr. John DeSantis. This project came out of a survey of one of our experimental unbonded concrete overlays. We were actually surveying this road and doing some testing for another project on performance of stabilized bases, and just happened to check this project out because it was a interlayer that we wanted to check out and see how it was doing after 5 years in service, and we ended up discovering a few things that we felt and IDOT felt were worthwhile in further investigating. Before I start the presentation on what we found in terms of longitudinal cracking, I will say that Illinois has a long history of unbonded overlays projects going back even to the 70s. They've had successful unbonded overlays, particularly continuously reinforced concrete overlays, and they've in the last 20 years done a large number of bonded concrete overlays of asphalt throughout the state, and those have also overall been very successful for medium to lower volume roads for various agencies. So what I'm presenting today is a particularly new experimental feature that was being used in Illinois. I would say probably one of the first times, especially on a major principal arterial, I-72 interstate near Springfield, Illinois. And so the findings here are what we've seen and tested to date. It was a special project, so we didn't actually, this wasn't a 2-year study, it was more like a 6-month study. And so at the end of this, I'll make some observations and conclusions, but by no means did we exhaust what we could have done just based on the time and resources we had to do what we did do. But we did discover some things that I think are useful to communicate. And I'm optimistic that we can continue to design, construct short jointed unbonded concrete overlays and see good performances. So that's my other note to start this off. Chuck Weinreich, was the TRP chair for this research project through the Illinois Center of Transportation. As you can see on that screen, there is, if you Google ICT publications, Illinois Center for Transportation publications, you can find the full documentation of this special projects R27 SB 48 that was published on February 4th, 2022. So this work was primarily done in the summer of 2022 to the end of the year, and summer of 2021, and finished up at the end of 2021 into 2022 when the report was published. And we had some students involved in helping out on the field survey, but primarily John DeSantis and I did most of the research and analysis of the data, et cetera. So today's outline will be just give you a background on I-72, the unbonded overlay, features, especially what we did in the field investigation, summarizing some of that. Also, we at the time, since we found some interesting things, we're also looking at other similar projects in different states to just kind of calibrate whether we thought what we were seeing was being seen by others or not seen by others. We have some ideas on the distress development mechanism, and then probably many of you are thinking, well, what do we do next? Do we put this to bed and never do it again, or do we what do we make adjustments on to make sure this doesn't happen like we're seeing it in this project? So to kind of start off on the project, this is, if you know where Springfield, Illinois, which is right in the center of Illinois, the capital, it's off here to the left of the map that you see on the screen. Here, and I'll get my pointer so everybody can see. So Springfield's is kind of located right here. Project's about 5 miles from Springfield, east of Springfield on I-72, which connects Springfield to Champaign. I-72 goes all the way over to the border of Illinois and Missouri, and it goes all the way to the border of Indiana, Illinois. Or excuse me, it goes just to Champaign, and then it connects with 74. This project was slightly, was around 4 miles or under 4 miles, about 3.2 miles, as you can see at the bottom there. It's a 4-lane divided highway that's been, I believe it was constructed in the mid 70s, and it was a continuously reinforced concrete pavement that had performed very well and had been overlaid a number of years ago. And that overlay was going to be taken off, and some repairs to the underlying CRCP were going to be done. And then the nice thing about this project that I think many of you will be interested in is on the eastbound direction, so away from Springfield, they used a 1 1/4 inch bituminous or hot mix asphalt interlayer. On the westbound, they used a nonwoven geotextile as the separation layer between the CRCP and the new short jointed concrete pavement. Another feature that's also included is macro fiber reinforced concrete. And this was an unbonded overlay. It wasn't a bonded overlay, which Illinois had done a lot, where basically you're doing short jointed slabs, primarily 6x6 panels on an existing asphalt pavement that's been milled or just put on the top or cleaned. This particularly was unbonded with an interlayer. In both cases, the separator layer was new, either geotextile or hot mix asphalt. And the existing asphalt, I believe, had some signs of stripping, so that's why they milled that off and put a new one down. The shoulders were also upgraded. Part of that was construction expediency, so you didn't have to have counterflow traffic. So this gives you an idea. This is eastbound, eastbound, the 1 1/4 inch separator layer that was done. First, the driving lane and shoulder were done, and then traffic was put, after the concrete overlay was done, then traffic was placed on it, and then the passing lane and inside shoulder were done. Likewise, on the westbound, you had the separator layer in the driving lane as well as on the shoulder, and then traffic was switched and the pavement was cast on the inside lanes. So this was quite efficient and saved a lot on traffic control. A lot of these photos that from the construction are from Randy Riley. Many of you may have known him, who was involved in helping see this project through or work with IDOT. As I said, the concrete batch plant was really right off the exit where this was being constructed, and this had 4 pounds per cubic yard of macro synthetic fibers, which was pretty much what we've been using in our bonded concrete overlays of asphalt. So nothing new in that regards. This did not have dowels. There was no dowels at the transverse joints, and there was a tie bar between the construction joint and the 2 lanes, which I'll show you in a second. So this gives you an idea of the driving in the shoulder. You can see this is a 12-foot lane here, 6x6 panels. This was paved monolithically. You have a contraction joint between the shoulder and the driving lane. The shoulder was the same thickness as the passing lane, or excuse me, the driving lane. And then subsequently that inside shoulder is a lot smaller, but you do have a 12-foot lane there as well. Obviously on the shoulder here, this was an asphalt, there's an asphalt layer on the shoulder, so you're putting your concrete over an asphalt layer. There is no CRCP, just in the driving and passing lane are the CRCP. So this was actually August 2020 when we did a survey just to look at some bonding responses and to see if we could detect bonding between the surface layer, the inner layer, as part of a separate project on performance of base layers or inner layers beneath slabs. And when we were doing that, that's when we discovered some cracking. This gives you an idea of the cross section because you really can't see it from the previous slide. So you have the 6 inches of the bonded or the unbonded concrete overlay. Those are all fiber reinforced over the shoulders, driving, passing lane, inside lane. Everything's basically 6 by 6, obviously a little bit shorter here and a little bit longer in the shoulder. Longer meaning it's probably more like 6 feet by 5 feet because it's a 10-foot shoulder. Your interlayer depends on the direction of traffic. You have your CRCP, and in your shoulders, some of the existing shoulders was left in place, and then a new base course was placed on top of that once it was milled. Both, you do have some edge drains functioning. It appears to be functioning depending on where you're at in the section, but there was no under drain work done as part of this project. So these are some of the observations. I have a lot more pictures, but this gives you some general idea. As we were walking in the early morning, because of the dew and the time of year, we saw the shadowing that particularly seemed to match up about 7 to 8 feet apart. So it appeared that right in the wheel pass, we were seeing these longitudinal cracks that were emanating from the transverse contraction joint and propagating in the leave and the approach slab some distance and then being arrested. And at times we just saw it on the inside wheel path, and times we did see it on the outer wheel path only. And it was a little bit of puzzling. I had contacted Chuck when we were doing this, Chuck Weinreich of IDOT, and said, hey, have you guys noticed these cracks? And they had said no. And about the middle of the day, it's almost impossible to see these unless you're really looking for them, because the dew kind of subsides and you really these don't light up because the cracks are so tight. So they could easily be missed on a survey if you weren't doing it at the right time with the right amount of moisture infiltrating those kind of micro cracks that are there. So we kind of knew something was different there. Weren't necessarily sure what was going on. We did find a survey in 2016, and the ironic part about that, there was a few of these cracks at the exact same locations we had seen them that had showed up on that survey. And so it seemed like some of these cracks started showing up pretty early, and the density of these cracks kind of vary along the 3+ mile section. And this, I'm showing the eastbound direction with the hot mix asphalt interlayer. We also took some pictures of the drains, and we're kind of formulating some hypothesis of maybe why some of these cracks were occurring. We weren't seeing any defaulting on the transverse joints. We weren't seeing any pumping on the joints. And the other thing that was very interesting was the passing lane had none of these cracks. So we could clearly see these in the driving lanes, and this had about 20% trucks. So it was around 1,600 trucks per day in one direction, but nothing on the inside. So it appeared to be load related, didn't appear to be related to pumping, at least initially. And because this had macro fibers, the cracks were super tight. Now we did note in a few locations that there was some faulting along this lane shoulder joint that was quite large, and that was a little puzzling to us as well. There was no transverse tie bar, there was no tie bar across that longitudinal contraction joint here. This was not a construction joint. The middle lane was the construction joint, the middle of the pavement. So let's so some of the observations that we made based on this experimental section was it kind of varied where we saw the longitudinal cracks. Some of them had higher densities than others. It wasn't on every slab, and sometimes, as it's shown here, we'd see 4 cracks over 1,000 feet, none in the outer wheel path, some in the inner wheel path. So there wasn't a consistency there that was helping us figure out what was going on here. We thought possibly, maybe the inner layer was deforming and compressing. But we did see clear signs that there was something going on in the driving lane, particularly because we didn't see anything in the passing lane. Now, we went over to the westbound later in the day, and as you can expect, we figured we'd see something similar if it was related to possibly fatigue cracking, because this was 6 inches like the eastbound. It was also obviously with the interlayer, it wouldn't have as much structural support. And we've seen from other projects that with interlayers, geotextile interlayers, that you may have to increase the thickness of these slabs because they may induce higher stresses in the concrete slabs. At least that's what others had reported in Germany, and even Kazanovich has that as part of his unbonded overlay design. However, we didn't see any cracks. So in the westbound with the geotextile interlayer, we did not see cracks anywhere. So no distress, minus the fact that, again, along the longitudinal contraction joint separating the driving lane and the shoulder, we did have some faulting going on there. So for some reason in both lanes, we have the shoulder pushing up or the driving lane falling down, one or the other. That was our initial observation. Both directions have fibers, and obviously whatever the displacements are between the driving lane and the shoulder were large enough that the fibers were actually not keeping the alignment between the shoulder and the driving lane. So that was a little puzzling initially. We did do some coring, which I'll explain a little bit later. So, we started developing some hypotheses. There's another picture of some of the cracks in the driving lane in the inner and outer wheel path on the eastbound direction with the HMA interlayer. Was this related to erosion or pumping? Was this something going on with asphalt stripping? Was there permanent deformation within the interlayer because the mixed wasn't the right mix, or had some high air voids that then compressed? We did know that IDOT did some cross slope adjustments with the HMA layer. Was that somewhat related? We're not sure at the time. And it appeared that there was more inner wheel path cracking in some sections. So was that related to some change in the HMA layer, localized drainage issues? So these are, we started generating more questions than we had answers for. And we, had some ideas from previous unbonded projects with short slabs that, or at least with generally unbonded overlays, that, cracking could occur if you had widened slabs at the edge, which we didn't have. If you didn't have 6 by 6, but let's say you had 12 by 12, you tended to see some longitudinal cracks. We did see some cracks in other states where there may have been in urban areas and the drainage wasn't so well with the geotextile fabric, but not with an asphalt interlayer. And we, Iowa had reported some longitudinal cracks or had some distress when the longitudinal joint was closer to the outer wheel path, which was also different than we had. So we didn't feel like there was a lot of similarities exactly with what we were seeing out there, but we weren't 100% sure because we hadn't really, collected a lot of the unbonded overlays from previous DOT efforts. So we went back into the literature when this project started. So this initial survey wasn't even related to the project, and that we started the project about 6 months later, and we found that some of the design methods that were out there, or at least being released, considered the interlayer, whether it was geotextile fabric or asphalt interlayer, but really no calculations related to its performance if that was the mechanism causing failure. We looked at some literature and found some cracking that happened in a Chinese study, but it had kind of a different outcome where the asphalt interlayer was doing better than the separation layer with the geotextile. SL there is the separation layer. And then some work done at Pittsburgh by Sachs. They mainly reported cracking in longer slabs, meaning longer than 6 by 6. So that wasn't really applicable to what we were doing. But there was some efforts done in some permanent deformation models saying that under repeated loading, that asphalt layer with the thinner concrete may undergo some permanent deformations potentially and cause some cracking in the overlay. So this would be the idea of that Suter study from Pittsburgh. And this was work done again at Pittsburgh by Sachs, where you may have some erosion in concrete overlays. One of these mechanisms seemed like it could be a potential reason for this happening. Initially, we focused on the interlayer deformation because we really weren't sure about the asphalt and its properties and whether it was put down correctly because it was kind of hidden. The other interesting feature about this project is you have not a jointed plane as the existing, but a CRCP. So you have a very well intact with tight cracks CRCP. So it's a plate with very little deformations and drainage that then has an inner layer and then a concrete overlay. So it may be slightly different than you'd have an old jointed plane that has a lot more cracks and joints in it that can drain water from it, potentially. So we started formulating that stripping and erosion, even though we weren't seeing anything, could be a possibility here. Another study from South America and Colombia had shown that even with stabilized bases, if you get water in there, and as you can imagine, that the classic pumping and erosion is where the material is ejected out of the joint, and it's in volumes where you can see it. Here, where you have asphalt, you're not going to eject large amount of materials. So what we may have here is an erosion of the layer enough that you get some higher localized stresses at the joints, and those create the longitudinal cracking. So we were kind of using Caro's study to kind of formulate an idea that although we weren't seeing pumping on the surface, we may be eroding the asphalt interlayer. And here was one other puzzling thing we found, just to kind of calibrate your thinking here, is we did FWD in the 2020 study, and IDOT had previously done FWD in 2016. And if you look in the eastbound direction with the asphalt, you can see the load transfer across the joints was pretty good, even in 2020. So that didn't seem like there was some joint LTE loss. The deflections, the total deflections at the joint were around 3 to 4 mils. So 0.1 millimeters, that's at 9,000 pounds. And then differential deflections at the joint were, less than 0.01 millimeters. So all these deflections weren't that large to cause major concerns. The other interesting part, if we look at how the eastbound and westbound performed, so the westbound was the geotextile interlayer. The funny part was the westbound, the LTEs were lower at the transverse joints. The deflections were higher with the geotextile interlayers, and you can see that at both the joints and the center slab deflections. So it wasn't, so the 2016 deflections were lower, the 2020 eastbounds were higher, but the westbounds were even higher. So we had to kind of explain that. Obviously, the fabric has some compressibility, so that's one way to explain the difference in deflections, given that it's several millimeters thick, and under a load, it's going to compress, and you're going to get that extra deflection. Another factor in the difference in deflections from 2016 to 2020 was the temperature. We did it in the middle of summer, and with a 6-inch slab, your asphalt's still pretty hot in the summer, whereas 2020 it was done in the late fall, I believe. So there was probably a big factor in temperature when we did the two different tests. So they probably weren't as different as it kind of seems from this picture. But still, there was a couple things that were interesting to note. The load transfer across the joint in the westbound with the geotextile was very low in 2016. It was still low in 2020. That joint load transfer was really high with the asphalt interlayer and got much lower by 2020. We're seeing faulting in both of those, so that seems to make a lot of sense. But as you can see, in the red here. In 2020, you still had this discrepancy in the deflection. So it's always good to make sure you don't completely translate your FWD deflections. The higher deflections means poorer performance all the time. In this case, the ones with the lower deflections are actually the ones that are cracking. We also did some MIRA tests to make sure maybe the concrete thicknesses weren't as per plan, and then generally the average thickness was greater than 6 inches. There was some areas where the concrete was not 6 inches, but it didn't appear to be related to where the cracking was, so we couldn't link inadequate thickness to longitudinal cracking. And in some cases, the interlayer varied in thickness, so it's not a surprise that the concrete varied. So as we're looking at the, so the next obvious step was to go out and do some coring. Our first coring plan, we went out and we cored over the longitudinal crack away from the joint, and we kind of went back from there to see if the crack was, how deep the crack would go and how far in the longitudinal direction did the crack propagate in the slab. You can see the cores we took that were in the 1, 2, 3 positions here. You can see the asphalt's fully bonded to the concrete there, and so that was a little puzzling. So we're getting longitudinal cracks, asphalt's bonded to the concrete. That's a little puzzling. That kind of dismissed this idea that this was erosion initially. We also cored in other areas of the slab and found the same thing in the middle of the slab, that everything was bonded. So our initial coring, which we didn't do that many cores, or IDOT did the coring for us, was that maybe there was some permanent deformation. That's how my mind was tracking this. But then we decided, well, I guess we should go back out. And so in 2021, after the project had begun, we actually re-cored only over the cracks and joints. So we wanted to see what was happening directly over the joints, and lo and behold, we found that there was some evidence of stripping in the asphalt interlayer, and we did coring on both the eastbound and westbound, so we could look at the interlayer, geotextile, and the hot mix asphalt. We also cored over the lane shoulder joint to see what was going on there, because we knew we were having some faulting across that contraction joint. So here's some pictures of some of the cores. You can tell that if you're away from the joint, the asphalt looked pretty good. It was bonded. Right when you got right over the joint, you can see that the asphalt is eroding and stripping. It's breaking down. We didn't see this material on the surface. You can even see in this case where the leave joint is beginning to deteriorate faster than the approach joint. And we saw that in several different cores, that the leave was much more deteriorated than the approach. In many cases, they were both somewhat deteriorated. So there was definitely some action with water and deformations that was causing this asphalt to deteriorate. And here's a few more across the transverse joints, some of them worse than others. Interestingly, though, as you get 6 inches from the joint and everything looks perfect. You have bonding and no stripping at all. So this is very localized over the joint. And and now IDOT uses no seal joints. They don't seal their joints, particularly on overlays. And so the question, is water getting out? Is it just kind of sitting in those joints? That's a fair question. We did see in some cases when we did the coring on the geotextile side, when we filled the core hole with water, the water would drain out pretty quickly. When we did that with the hot mix of asphalt interlayer, the water would not drain at all very quickly out of those cores. So there seemed to be a lack of drainage path for the water once it got into the joint and below the slab, which is going to tie into one of our mechanisms. This is kind of a picture inside the core hole. The damage isn't extreme inside the core hole, but you do see some erosion and stripping of the asphalt layer around that joint area. And you can see on the left here, the longitudinal cracks are very hard to see, even in 2021. So it's not surprisingly, people would go out there and miss these cracks if they're not lit up. This was the coring over the longitudinal joint that was showing some faulting, and you can see there was a lot more disintegration of the asphalt, and that was a lot more significant. And so we're seeing the fibers sheared off in those locations. The HMAs are eroding much faster, and so there definitely appears to be an issue with water that gets in and can't get out, and then it becomes pressurized with a significant amount of repeated loading from truck traffic. And that's why we see the cracks in the driving lane and we see no cracks in the passing lanes. So one of the mechanisms that we came up with was along this shoulder joint, some of the materials being eroded under that shoulder and pushing the shoulder up. That's a hypothesis. It seems to kind of fit in with what we're observing. That can be as high as a ½ inch, but most of the time it's about a ¼ inch. So this water pressure along with material being pushed under the joint seems to be what's lifting the shoulder up. When we did some Google surveys and talking to various engineers throughout the U.S. that have done short jointed slabs, we did identify projects that did have longitudinal cracks. Not all of them. The problem is not all these longitudinal cracks have the same features. They may have different pavement types underneath that are causing these cracks that are unrelated to what we're seeing. But we wanted to get some sense of how frequently we would see these types of longitudinal cracks on similar 6x6 panels. And we did see some, and that's one of the downsides of this study, given it was short. We can't really map whether some of the failures in other states are exactly like this without, a more deeper investigation. Not all projects had this type of cracking either, so that's another factor in there. We did drive up to Michigan. Dan DeGraft gave us some sections that were similar, not exactly the same, that had interlayers and asphalt mixture interlayers, and he had communicated that they had seen some hot mix asphalt erosion and stripping, and that's why they had went to the the geotextile interlayer. Likewise, we had heard the same message from a conversation with John Donahue down in Missouri, which is their reasoning from going to a geotextile interlayer. So there seemed to be anecdotal experiences that were suggesting that this erosion of the hot mix asphalt, especially when water gets trapped beneath the slab in the interlayer, was causing premature cracking, particularly longitudinal cracking. And you can find the report, and we go into a lot of the sections that we kind of looked into. We did talk to Dr. Manick Barman up in Minnesota, who ran out and looked at T8 trunk highway 53 that had some longitudinal cracking, and he took some pictures and gave us some information on that particular 6x6 project. So in summary of our field investigation, both what we did in Illinois and other states, that there were some longitudinal cracking present in surrounding states. It may be related to the same mechanism, maybe not, but at least we do observe it. And it is one of the mechanisms in the unbonded overlay design, because that's the highest stress point, even without any type of erosion. But we do think it's if we're getting water in and the drainage path out of the pavement structure is not clear and quick, that there is a likely cause that the dense graded hot mix asphalt is actually stripping. Maybe not very quickly, but it is stripping. So the one in Illinois is 7 years old. If you drive over it, you'll never notice there's any problems with the pavement. So there's not observable feeling to the driver yet after 7 years. So how long it'll last without any significant distress that's causing a user discomfort in the car is hard to tell. We do see that the fabric interlayer, at least on the project we did and some of the other projects, seem to get the water out underneath the pavement. We do still see a faulting across the longitudinal contraction joint on the geotextile interlayers, and that's still a little puzzling. That if I have the opportunity to go out and do some more coring, that's probably an area where we'll look into of why are we seeing geotextile interlayer have a faulting across the shoulder driving lane joint. Could be because some, again, pushing incompressibles under that shoulder and lifting it up. There's no tie bars there at that shoulder lane joint, so that's another reason the fibers maybe just aren't stiff enough to keep those aligned. One thing we wanted to do, since we started panicking that maybe all hot mix asphalt projects are showing the signs of erosion, we noticed in another project built a few years ago down in southern Illinois, a jointed plane that they use an asphalt interlayer. And what we went down to that project because we thought there was longitudinal cracking, and it turned out we did see longitudinal cracks, but they were over the dowel bars and unrelated. I believe this was a dowel bar inserter project, and it appeared that in several locations, along with some locations of the tie bars, there were some cracks happening over the reinforcement. So it wasn't a systematic problem, and this project actually was doing all right, even though it did have an interlayer, had a longer joint spacing. Interestingly, this is a lot more hilly. The drainage was very good in this area, and there was no sign of pumping, no sign of other distresses, and of course it had dowels across the joints as well. But there was generally no distress that was related to repeated loading, at least. One thing that we started looking in the other project and then looked back on this project was the asphalt interlayer substandard. And IDOT had originally done testing on this material, and it had passed their standard Hamburg wheel test, tracking device test up to 20,000 cycles, which actually is even more than they require. So it did not, at least in terms of rutting performance, it doesn't really measure stripping, but it can be an indicator of stripping if the asphalt breaks down. But at least this particular mix that was used was not out of spec and passed IDOT standards for their performance test with the Hamburg. So if, for instance, we implemented this for asphalt under concrete, we wouldn't have found that this asphalt was a problem. That's what essentially this is saying. We looked at some design methods and went through them and to see if it would have predicted failure of these sections based on the traffic, and we also obviously came up with the conclusion that they wouldn't have predicted what we saw. Obviously, unbonded overlays with short joints are still relatively new design, and most of them deal with the structural analysis of the plate and the underlying support, but not in the performance of the interlayer. So looking back at our questions, this is kind of where we're at. I don't have all the answers to the questions, but we do believe there's a combination of erosion and stripping of the interlayer. I guess it's kind of combined. You have to have, it appears you have to have water, you have to have repeated loading by heavy vehicles, just not passenger cars. It's slow. It doesn't appear that we have permanent deformation in the interlayer yet. It may happen if you get enough erosion, I guess. And I guess it may be happening in the localized area by the joint. I don't think this failure has anything to do with joints not activating, whether that's longitudinal joints or transverse joints. And why the inner wheel path in some sections seem to have more longitudinal cracks could be related to the drainage pass. You have to drain a lot further from the inner wheel path to the shoulder. And we may have some issues with the shoulder here such that the water isn't able to get out as quickly as it needs to. So maybe there's some changes that need to be happening at the shoulder so that water gets out once it hits that shoulder interface. So this is kind of the mechanism that we kind of ended our study on, that and this was only in a way to kind of explain what we think's happening and then think about how we could kind of minimize this from happening in the future. We have very impermeable CRCP. It could be a jointed plane, but CRCP is particularly impermeable. Then you have a very impermeable asphalt interlayer that doesn't provide a drainage path. And then water gets in, and that water can get very pressurized under heavy loading. If it has nowhere to go, it tries to go horizontally. It can go vertically as well. But that abrasion factor, because also dust and debris are getting in those joints, start to erode the asphalt, either at this interface or at the interface between the existing concrete pavement and the interlayer. And so that's the beginning of where these longitudinal cracks start, and they have been propagating not very quickly. So your question now may be, well, what do we do about this? We don't want to stop using unbonded overlays. Could we use a more erosion-resistant interlayer? I'm not sure about that. We'd probably need to do a lot of testing, which we didn't have time to do. The fabric interlayer seems to be working, and it was a good application with the CRCP because the CRCP is not moving underneath that. Fabric interlayers may not work in every application, but it seems to be working there, particularly because it's clear water's getting out in the driving and passing lanes. It doesn't appear the HMA interlayer was substandard by any means, so that can't be seen as the problem here. Well, the other idea is to minimize moisture infiltration and make sure that if water does get in, that it can have some subsurface drainage pass out of the shoulder or out of the driving and passing lane into the shoulder. There's many ways to look at that. I'm not necessarily saying you need to have a permeable interlayer necessarily, but at least enough cross slope to get the water out and out of the shoulder or into the edge drains. Obviously, putting some tie bars across the lane shoulder joint would probably be a nice option in the future to prevent any type of differential movements or settlement that may occur over time. Maybe sealing the joints, although that's a lot of joints to seal, and that makes it less attractive. As the traffic volume gets higher and higher without sealed joints, yeah, you may have to think about dowel bars, but maybe that doesn't make sense for 6x6 slabs. So those are some of the thoughts I currently have on what to do with 72. You could obviously overlay this or just continue to monitor this. These are kind of my ideas, not IDOT's necessarily. They're not necessarily going to do this. Maybe you could seal the joints in the driving lanes right now to kind of slow down things. That may or may not work. And in the future, it's possible that if we redid this, we may try a few different strategies. Obviously, the interlayer with the geotextile seems to be doing well. So if that can be used and there's no cross slope issues and there's no reflective cracking issues, then the geotextile interlayer seems like a good choice. But at other times, it still seems like if we're going to do unbonded overlays with short slabs, we're going to have to use asphalt just because of its ease of use and the elevation restrictions that we need to correct. I will say again that hot mix asphalt interlayers on CRCP overlays have performed very well in the 40 plus years Illinois has done it. So there's not an inherently bad performance problem with hot mixed asphalt interlayers. For this short jointed slab without dowels, with a lot of joints, maybe we've got to rethink a few things about how the water's getting and how the water's getting in and how the water's getting out, especially under the higher deflections that can pressurize that water and cause stripping. And there's some tests out there that I'm not going to go into, but that can look at more pressurized stripping effects. So I'm right at my time limit, I think, so I'm going to stop now and take any questions.
Hey, Jeff, this is Jay Benke of State Testing. First of all, very, very good presentation. I appreciate your methodology of looking at all possible, avenues of, the failures. I guess my one question back to the HMA interlayer is I'm glad you guys looked at the Hamburg. Just curious, it didn't appear from the graph of that Hamburg that there would have been a stripping inflection point calculation. It looked pretty flat, but I was just curious, let's face it, I know, Iowa has developed that, and the Illinois Tollway uses that. I was wondering if that calculation was done on it. And then also, just the old standard T283 or Illinois modified, District 6 did any of that testing just to make sure that, the mix didn't have, any stripping potential, or if, a chemical anti-strip agent was used.
Yeah, thanks, Jay. I can't comment on the stripping calculation, but Greg Heckel vowed that this was not a strippable mix. I don't think there was anti-stripping added to that at all. And I felt pretty comfortable talking to him, and the data I saw that this was not a mix that if you put it on a surface and would drive on it was going to rut or strip. And we had done some other Hamburg tests for interlayers for this other project at our lab in Rantoul, and saw other asphalt mix that did strip and didn't meet IDOT's criteria. So we felt like, okay, the data that we've gotten from IDOT and for the mix at that particular location doesn't appear to be one of those susceptible mixes.
Got it. Thank you.
I see Bernard's hand up, and so we'll take his question and then go through some of the questions in the chat.
Yeah, thanks a lot. Can you hear me?
Yes.
Yeah. Okay, thanks a lot, Professor Roesler. I have two questions. Very interesting study, by the way. These are the kind of studies that are very helpful because they go into the real issues. First and foremost, your factorial was limited to CRCP, which is a little novel because you are using JPCP on CRCP. It's not a very common animal, but the idea, the fact that the drainage issue comes into play, I think that's a very, very important note in the sense that the CRCP does not provide the kind of relief that you may have if it was a JPCP, JPCP on a JPCP, but you have a JPCP on a CRCP. So it's not in Minnesota, that's not a known animal. I mean, it's not very common, but it's an area to take note of because unbonded overlay for the preservation of our concrete in the system, in our networks, we should be looking at unbonded overlays. So it's good to know how unbonded overlay will work on a JPCP. But the other aspect I wanted to ask is, in this factorial, there was no mention of PASRAC at all, the permeable asphalt stabilized stress relief layer. Instead, you use a normal HMA. How would a normal HMA ordinarily give you stress relief? I mean,
Yeah.
Reologically, so I was just wondering, was that just an Illinois decision? Then the other thing you can, I want you to comment on is, there was no IROI measurement. I mean, is there, or could it have been, you didn't mention it, but could there have been IROI measurements? Because this can also lend credence to some of these things that we are observing. Those are my questions and comments. Yeah.
Thank you, Bernard. Yes, we did talk to people about permeable asphalt layers. I won't mention who we talked to from various states, but there was, at least the conclusion was, some people talked very highly of them and some people did not talk so very highly of them. And so it seemed like the experiences with permeable layers, even though they sounded good and performing for the same state, different engineers would have different conclusions, and that would be in multiple states. So it's not just one state. And so IDOT doesn't use a permeable layer, interlayer. They had used permeable base layers in the past and had subsequently not used them anymore under concrete. As a note, there are IRI numbers for that project, and I don't have them at the tip of my hand, but it's pretty good. I think it's 80 or 90 for this overlay. Somebody asked in the chat, the tie bars were only in the center line joint between the two paving lanes. So it was the only construction joint in the middle there. And the joints were not skewed, even though it looked like it.
Hi, Professor Roesler. This is Deepak Maske from Caltrans. Do you hear me?
Yes.
Hey, I have a simple question regarding the pattern of these longitudinal joints. So you have a slab 6 by 6 inch, and in 3 areas, in inner side and transverse side, it is a kind of interlocked, a kind of restraint there. But adjacent to shoulder, there is no interlock. There is a free. So in other words, in one part, it's kind of a cantilever. So do you think that could be the reason getting longitudinal joints, because one side is a kind of little flexible, and you have HMA, which is supposed to be flexible. So there is a movement, vertical movement in the HMA interlayer. So do you think that could be the effect on this transverse in having a longitudinal joints?
You mean longitudinal cracks?
Longitudinal cracks, yeah.
Yeah. Well, we're pretty certain that most of the longitudinal joints cracked, the contraction joints, and so yeah, I'm not sure I would go along with that theory that's where the cracks are. I mean, because you have the same problem in the passing lane and you have no cracks. So what would make it preferential on one side versus the other? There's zero cracks in the passing lane and shoulder, so I don't think it's related to that at all.
Thank you.
The geotextile interlayer is probably maybe 3 to 4 millimeters, maybe 3 millimeters.
Hey, Jeff, you know, I always say that, you know, concrete overlay does not have to be thin. It should be designed for whatever traffic you have. And I think that in the interstate, I don't know what the traffic, you know, was there, but I would be concerned with like a 6 inches. And I think that, you know, the thin slabs, I'm sure you must have done some finite element analysis, but a thin slab with no dowels, your critical stresses should be the transverse creating a longitudinal crack.
Sure.
So you talked a lot about the interlayer, but I think it may also have something to do with the thickness and the location of the critical stress that's creating that longitudinal crack.
Yeah, I agree that if you do an analysis, the highest stresses will be at the transverse joint in the longitudinal direction. The crack would propagate, and that other people have found that. So that's, yeah, that's a good point. However, if you do an analysis with trucks with that structure, you wouldn't expect this to fail this quickly. You would expect this to last 20 years. So the thickness, the question would be, well, if I had a thicker slab, would I have avoided all the cracks? Well, that would depend on whether the primary reason for these cracks are thickness or erosion and stripping. I think if it's erosion and stripping, maybe you delay the cracks a year or two, but I'm not sure that you would have prevented the cracks from occurring even if you had a thicker slab, given that it's clear the asphalt in some locations has significantly deteriorated into rocks and binder kind of separated. I think Tom Burnham said something, unless the shoulder is entirely unbonded, it's difficult to believe that the slab lifted by the HMA materials ejected from the driving lane, that he may be right. I don't know. I can't prove. I have a mechanism. I may be wrong. Clearly, both shoulders, whether it's an HMA layer or a geotextile interlayer, the shoulders are higher than the driving lane. What's causing that? I'm not 100% sure yet.
Maybe the lack of tie bars.
Well, the lack of tie bars doesn't cause something something either has to go down or up. I agree. The tie bars, if they were there, maybe you wouldn't notice it. But what's causing it to go up or down is the question. Particularly in the interlayer. I mean, how is the interlayer, geotextile interlayer, causing a faulting to develop? If it's working nicely, the water's getting out, why is the shoulder going up or down relative to the driving lane? The density on the asphalt was fine. We checked all that, multiple cores. That wasn't an issue. It wasn't too low either. And there wasn't, the mixture properties, the binder content, the in-place density was within typical IDOT specification. So we really couldn't link anything to the asphalt mix per se.
Justin also has their hand raised. Justin, if you wanted to jump in and ask your question.
Yeah, thanks for the presentation. We talked like 2 weeks ago, actually. I'm from the Michigan DOT. And I was talking about thin pavements and fibers. Anyway, just a footnote, I guess, regarding the Gratiot Road or Gratiot Avenue project in Michigan. We actually had some issues with some thin concrete sections out there. So particularly at the driveways and some intersections, they were actually lower than our specified thickness. So I think that was part of the issues we were experiencing with some of our crack slabs. So just something, I guess, I think you mentioned that in your table, that maybe not all these issues are related to the interlayer, but I think at least some of our issues may be related to not getting the specified thickness.
Yeah, and thank you, Justin, for reminding me. The tables I did list does not necessarily mean that they had the same failure modes that I demonstrated. Some of those projects clearly had cracking unrelated to what I did. What we saw at Illinois' experimental section.
Hey, Jeff, just another comment. You know, I'm not an expert in asphalt, but it seems there is a lot to be, I'd say understand, you know, a lot to be understood about what happens with stripping. When does it happen? I know there is, I believe, because I was actually like, talking about you know, with the experts here at Caltrans about it. And I know there is a NCHRP synthesis that was recently published about it, but that certainly, you know, from what you show, that seems to have had been like a problem, you know, eroding that HMA layer. So
yeah, and one thing we found on the other project we're not talking about now is the Hamburg. For some of our bonded concrete overlays, I know you don't like those terms, Dilse, but bonded concrete overlay of asphalt, I can't get rid of it. We found some of the projects that failed prematurely actually had, when we tested the asphalt in the Hamburg, would fail Hamburg test per IDOT standard. So clearly in cases where the asphalt was strippable, the Hamburg identified it, and we shouldn't have built probably those overlays on top of those hidden layers once you mill them off. But in this case, it didn't do it. And so was that because you have this extra amount of pressurized water under the slab that just can't get the water out, and it's a new mechanism that we hadn't thoroughly thought about. Well, people have thought about it. I don't want to say that, but maybe permeable layers underneath the layer makes sense. How you make it permeable, that's kind of the challenge. But
hey,
really,
and you don't have an interlayer. Hey, Jeff, you don't have an interlayer, you don't have a foundation, you don't have a pavement, right?
That's right. That's right. I think the challenge here is, where do we use these overlays? When are they applicable and fairly cost effective? And then where do you have to upgrade to some higher type of overlay, as Dulce was saying, that maybe a sticker that has dowels, that has sealed joints? I mean, there's a cutoff there that's not well defined yet. But I think, like we found with bonded concrete overlays of asphalt, we learned a lot 20 years ago that we don't do anymore. And so maybe in a few years, we learn a few more lessons learned and avoid certain practices that we know kind of may lead to premature failures.
All right, well, we are just 1 minute past the hour, so I think we'll wrap it up for today. But it sounds like that was a great discussion and great content. So thank you, Jeff, for your time, and thanks everybody for joining us today. And we hope to see you next month with an asphalt project.
Thank you. Appreciate it.
Mm-hmm.